Outliers, IQR, and Z-scores. So this is continuing on the conversation of finding a box plot, which we've mentioned how to find those 5 number summaries in your calculator. So what you're finding with those are your quartiles. So before that, though, we have fractiles. They're numbers that partition or divide an ordered data set into equal parts. So there's more than just quartiles. Quartiles just specifically means that we're breaking something up into 4 equal parts. So you have your first quartile, where 1/4 of the data falls on or below Q1. Your second quartile, which is where your median is at, that means that is the halfway point in your data set. So half of the data falls on or below. And third quartile means 3/4 of the data falls at or below. So keep in mind with 4 equal parts, each one of these pieces is worth 25%. So finding quartiles. This example says each year in the US, automobile commuters waste fuel due to traffic congestion. The amounts in gallons per year of fuel wasted by commuters in the 15 largest US urban areas are listed. Find the first, second, and third quartiles of the data set. What do you observe? Now, technically, we know how to find this with the calculator from our previous video, but I'm going to show you how to do this one by hand. So when you have a data set, to find those quartiles, you need to put them in order. So looking through this unordered data set, looks like our smallest number is 11. So we'll write that one first. Then we're going to slowly put all of these numbers in order. Now, when you type all of this in your calculator, you could sort the data in your calculator. But even if you didn't sort it and you use one of our stats to find these numbers, your calculator is automatically doing this in the background, putting it in order before it finds those 5 number summaries. So you don't have to worry about having it in order when you type it in. It does that for you. But if you want to do it by hand, you have to first make sure it's in order. Smallest to biggest. All right, now that we have all of our data in order, the first thing you want to find is your median. So you want to find your dead center. Now, because this is an odd number data set, there's 15 items here, there will be one thing in the middle. So I'm going to start counting in 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 more in. There it is. There's our dead center right there, 25. Now, I like to kind of count in from both sides, like count in 5 on the left, 5 on the right, 2 more in, 2 more in, until I get right to the middle. It just kind of helps me balance it. You could also do tick marks as you count your way in to find that true middle, and you could check it. There's the same number of numbers to the left as there is to the right of that dead center. So this in the middle is our median. We could also call it our Q2. Now we need to find Q1 and Q3. So what that is it's the median of the first half and the median of the second half. And we do not include the median in finding this. So I'm looking from 11 to 25. There's 7 numbers here. So I want the dead center, which here is 23. That would be the Q1. It is the median of the front half. Same thing on the back half. There's 7 numbers. So the one in the middle is my Q3. Once I have found my quartiles, then I like to go in and go ahead and identify my minimum and my maximum, because those are still part of the process when you're trying to find your medians. So I just wait to the very end to make note of them because they wouldn't be pulled out when I find them. So this is the same 5 number summary you would have gotten from your calculator. So once we have it, we can find what's called the interquartile range, also abbreviated as IQR. It's a measure of variation that gives you just the range of the middle portion, which is about half of the data. So this is great for data sets that are skewed, because when you have something skewed, you might have outliers or something that's pulling your data farther away than what everything else looks like. So interquartile range kind of cuts that off and looks at that middle 50%. So to do that, we're just going to find the difference between the first and third quartiles. So this is the formula. To find IQR, you take Q3 minus Q1. Now, once you have the interquartile range, we can use it to find our outliers. Previously, we just found outliers just by glancing at the data set, looking for something that just doesn't belong. But this is going to be used because maybe the number that doesn't belong is just outside the range that is not an outlier. So it's kind of hard to tell the closer it is to the rest of the data. This is the clear marking of what would make an outlier and what would not make an outlier. So the first thing you need to do is find that first and third quartile of your data set, then find that IQR range. Once you have the IQR, you're going to multiply it by 1.5. This is part of the definition. So that's for every problem. It's always 1.5. And then you're going to do two things. So I'm going to pop up both 4 and 5 at the same time because they're doing the same step in opposite directions. So on the left-hand side, you take Q1 and you subtract the number you just got from 1.5 times IQR. And on the right, you take Q3 and you add to it that same number, that 1.5 times IQR. Any entry less than on the left or greater than on the right would then be an outlier. So let's see this in action. Find the interquartile range of the data set from our first example. Are there any outliers? So just as a quick reminder, Q1 was 23, Q3 was 30. So to find the IQR, we are subtracting those two numbers to get an IQR of 7. Now our next step is to take that 7 and multiply it by 1.5. So 1.5 times 7 gives us 10.5. This is the number that we are adding or subtracting to either one of the Q1 or Q3s. So keep in mind what your box plot looks like. This is Q1, this is Q3 over here. So on Q1, we are subtracting to go to the left. So we're doing Q1 minus 1.5 times IQR. So that looks like 23 minus 10.5, because that's what we got when we multiplied 1.5 times IQR. So if we subtract this, we get 11. So then you ask yourself, is there any data in our data set smaller than 11? If so, it's an outlier. If not, we keep on going. Now we do the same on the other end. Q3 plus that 1.5 times IQR. So in that case, that looks like 30 plus the 10.5, which gives us 40.5. And on this end, you would ask yourself, any data larger than 40.5? So you check yourself on both sides. You check to see if you have something smaller than that lower number or something bigger than your bigger number. Anything outside of that range is an outlier. So if we actually go back and look at our data set, our maximum was 35. So we have nothing bigger than 40.5, but our minimum was 11. So we do have something, oh, I'm sorry, that should have been 12.5 here. So do we have anything smaller than 12.5? And the answer is yes. We have the number 11. That was me thinking ahead there a bit. That is your outlier. So you would have answered this question as yes, I have an outlier of 11. So percentiles and other fractiles that come up often. Quartiles, like we just talked about, were 4 equal parts. Deciles are 10 equal parts. That comes up sometimes. And percentiles will come up for you a few times in your homework, 100 equal parts. So oftentimes they write them as P1, P2, P3. This range, say we had P4, that's the same thing as saying 4% or the 4th percentile. And we're always measuring to the left if we were looking at a normal curve. So here's some percentiles to look at. This is a graph of one. This is an OGIF represents the cumulative frequency distribution for the SAT test scores of college-bound students in a recent year. What test score represents the 80th percentile? So on the left, we have percentiles, and across the bottom, we have scores. So if we find 80, and we trace it across, find where it hits our graph, and bring that down, it looks like we're hitting right between 1200 and 1300, so 1250. So we could say that the 80th percentile corresponds to a score of 1250, or we could say that approximately 80% of the students had an SAT score of 1250 or less. We're always measuring towards the left-hand side if you're thinking of a number line. So always or less. So sometimes you might have a data set and you want to find the specific location of one number among the list. So this is to find a percentile for a specific data entry. So this is the formula here in red. To find the percentile of a specific number, it is the number of data entries less than that number divided by the total number of data entries times 100, and then round it to the nearest whole number. So we'll make it a nice whole number percent. So this one says for the data set below, find the percentile that corresponds to 37,000. This is coming from a word problem out of the textbook that has tuition costs in thousands of dollars. So instead of 37,000, they just switched the number to 37. So all of these, even though they're two digits, technically are representing thousands of dollars. So they went ahead and put the data in order for you. Again, you could put it in order by hand, or you could use your calculator to sort it. So in order to find this one, we need to find the number of items that are first less than that 37,000. So if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers. Keep that in mind, 13 numbers less than 37. And we also want to know the total sample size here. So I'm going to keep counting, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have a sample size of 25, and we're also counting the number of numbers smaller than 37, so that's 13. Take that off. Times 100, this will give us our percentile. So 13 divided by 25 times 100 comes out to a nice whole number for us, 52%. So what that means is that the tuition cost of $37,000 is greater than 52% of the other tuition costs. So 52% is less than that $37,000 for tuition costs. Now, the other piece of information to cover in this section is Z-score. This is a formula that we're going to see now, and it's going to continue with us through the rest of the semester. So a standard score, also known as a Z-score, represents the number of standard deviations a given value X falls from your mean. So it's kind of like you figuring out how far your X is from your mean, how many standard Z-score spaces you are. So keep in mind your normal curve. We're talking about these bars. So this is your mean in the middle. I'm going to make a little squiggly line on it. If you ended up finding a Z-score of 1, it means you are 1 standard deviation away. A z-score of 2 means you are 2 standard deviations away, and so forth. So here's our formula. Z equals x minus mu over standard deviation. So x minus your mean over your standard deviation. So here's one to practice with. It says the mean speed of vehicles along a stretch of highway is 56 miles per hour with a standard deviation of 4 miles per hour. You measure the speeds of 3 different cars traveling along the stretch of highway at 62 miles per hour, 47 miles per hour, and 56 miles per hour. Find the z-scores that correspond to each speed. Assume the distribution of the speeds is approximately bell-shaped or normal. So they give us our mean. They give us our standard deviation. And then these 3 right here are different x values. And since they give you 3 different ones, you're really doing this 3 different times. So just a reminder of the formula. We could plug in our first one, 62 miles per hour minus your mean divided by your standard deviation, and we get a 1.5. Because it's positive, it means it's to the right, 1.5 standard deviations from your mean, which makes sense. 62 is a little bit bigger than 56, which is the center of our curve. And now we can do it again for the other 2. So the next one is 47. So 47 minus 56, the mean, divided by your standard deviation of 4, gives you negative 2.25. So that would be to the left of the curve, to the left of the hump. And our last one, 56 is our x, minus our mean, divided by our standard deviation, right where we would think it would be, right in the middle. When your x and your mean are the same number, your z would be 0. No distance from the mean. So this example says, the table shows the mean heights and standard deviations for a population of men and a population of women. Compare the z-scores for a 6-foot-tall man and a 6-foot-tall woman. Assume the distributions of the heights are approximately bell-shaped. So everything in our little chart is talking about inches. So quick math here, we got to switch 6 feet into inches. So 6 foot times 12 inches in each foot gives us a height of 72 for this man and woman. So if we use the same z-score formula, x minus mu over standard deviation, we've got 72 minus, and we'll do men first, 69.9 divided by 3. So when you subtract, then divide, we get 0.7. Not that far off. It would be reasonable to see a man who is 6 foot tall. Now let's try women. So same z-score formula, we'll plug in 72 inches for our 6 foot tall woman minus our mean divided by our standard deviation. We do this math, we get something a little bit bigger. We get 2.96. Now, there is a range where we can say conclusions about this, whether these answers are usual, unusual, or very unusual. So there's kind of a scale to it. If your z-score is anywhere between -2 and +2, somewhere in here, we would say that it's a usual score. So for men, it is usual to see a 6 foot tall man. Now, if you get a z-score between 2 and 3, or between -2 and -3, we would say it's unusual. So that would be our case here with the women. This is unusual to see a 6 foot tall woman. And if you have anything smaller than -3 or bigger than +3, that's very much out to your outer ends of your normal curve, we would say very unusual.